Hi, Alice. Hey, how are
Hi,
you?
I'm good. How about you?
Okay, good. Today, well, I'll finish the last of this simple harmony oscillator, and this Friday, I'm gonna just walk through the worksheet with you, the print too.
Okay.
So if you have more of that worksheet from school, just feel free to email me before this Friday. I'll just include it as part of the worksheet for this Friday review. Okay. So anytime before Friday, if you have more, then just email me. I'll take a
Yeah.
look and we can work through this Friday. Do you have any question about any part of our discussion, the last session or before?
No.
Okay. And the last topic in the simple harmony oscillator is forced um, harmony oscillator. So I'll quickly look through that chapter, I mean the topic, and then I already recorded the some of the example. I will just turn on the video, and then I'll just show you the my video script of the example problems. And meanwhile, while you're actually just watching the video, if you have questions, just ask me right away. I'll just stop it and then just answer your question. Okay.
Okay.
So let's quickly finish up force harmony oscillator part, and I'll move on to the next example problems. Okay, let me share my screen. Share my screen. Okay, so yeah. Okay. All right. So the force harmony oscillator is the harmony oscillator with the external force. So I gave you some, like one example with the spring constant K with the moving object M. So that is same as simple harmony oscillator, but there's driving force make a system continuously running. So if the mass M attached to spring with the stiffness constant K, and the surface of the ground has some amount of frictional coefficient. But previously, the two harmony oscillators, the damped harmony oscillator and the simple harmony oscillator, they basically just there's was some assumption that the system already start with some motion. So if driving force, I mean the damping factor is dominant, then amplitude of this motion is getting smaller and smaller and smaller and just gradually fade away. But if you have some kind of driving force exerted on the system, for example, you have some kind of like a motor connected to this M, and that's kind of like rotate, and that's gonna like push this M mass with the spring constant K. Then this external force F continuously provide energy into this system with the frequency F ext. So even with this kind of frictional force over the surface, rough surface of ground, because of this driving force, this M can continuously actually move. That amplitude doesn't have to be vanishing or just fading away. So if you do not, if the system has their own the frequency, which is the angular frequency 2 pi f, then their system frequency is determined by the spring constant K and the mass of this object attached to the spring. as we already know, this is intrinsic frequency of the simple harmonic oscillator. So there's no perturbation, there's no damping, there's no external driving force with the external frequency. But once it's attached to the external driving force, then this external force enforce that system oscillating with the external frequency. So without external force, there's some kind of like intrinsic frequency, and their maximum frequency, the maximum amplitude of the simple harmonic oscillator normally appears when the frequency is sitting on the this condition, square root of the k over m. So when this frequency, this is x-axis is the frequency, and the y-axis is the amplitude of oscillation, so the xt. So without perturbation, it's supposed to have really sharp peak without the damping. If frequency, the oscillation frequency is same as the intrinsic frequency of k and m, then there's only one single frequency component right there. But because of damping out of rough surface, there's more actually this resonating behavior actually just more broaden over a wider frequency range. So if your external force, external frequency is just scanned from some zero all the way to the maximum frequency, so you get gradually increased, then the system responds with respect to the external driving frequency. And when it's actually same as f naught, so basically f external same as f naught, then it's perfectly actually resonating. The resonating means like external force frequency, external perturbation is exactly same as intrinsic frequency of the k and m. Then there's no energy loss. All the energy actually transfer from the this external force onto the system. Usually, if external frequency is not same as the this resonance frequency, there's always some amount of energy loss to this surface loss. So the surface friction. But even with the surface friction, if the frequency of external force is exactly same as resonance frequency, or like intrinsic frequency of this k and m system, then the energy loss should be the minimal or zero, right? So that is called the resonance. That is x frequency is approximately same as intrinsic frequency, which is 1/2 k over m. In this case, amplitude can become really large, like an overshooting, when the driving frequency near the natural frequency or intrinsic frequency of the system, as long as the damping is not too large, right? So the frictional force is not dominant, is not large enough, then at the resonance condition, so external frequency is same as the intrinsic or natural frequency, this magnitude of this displacement will be the maximum or the largest. So that is called also resonance frequency. So resonance frequency, same as natural frequency or intrinsic frequency of system of the force harmony oscillator. So if you want to just analyze the this force harmony oscillator into some equation form, then you can apply the external force into Newtonian system, Newton's law. So external force could be formalized with the finite number of the force times cosine omega t. So the omega is the frequency of external force. External angular frequency. And now you have this amount of force added into the system. Previously, in isolated system of Newtonian coordinate, then that should be inertia frame, actually, that is F equal ma. So that should be equivalent to spring force based on the Hooke's law minus the frictional force that out of the viscosity, plus now we only have these two terms previously. This first term is for simple harmonic oscillator, and second term is damped harmonic oscillator. Now we got to add external force, driving force, which makes the system continuously actually run. So these two, first term and second term, restoring force. So if you just convert it into the two second degree order differential equation, then that acceleration should be replaced with the second order derivative of displacement in time. And now we just move that everything to the left hand side or right hand side, maybe here. That should be m times d2x over dt squared plus kx plus bv. Or you also have to just convert the v velocity of this up the mass m with the dx or dt. So let me just rewrite it. Then that should be b times dx over dt plus kx is the f naught external force cosine omega t. So this is nonlinear second order differential equations because you have cosine function added into this formula. So that is second order nonlinear differential equation. So I'm gonna skip that. Actually, just the derivation of this one is you need like a more mathematical technique to solve it. But its solution is actually already well known. So let me give you the solution format, which is x equal x maximum sine omega t plus phi. So this external driving term change the phase of the displacement. So because that starts with some amount of actually displacement, so this external force create the the displacement with the sine function. So previously, simple harmonic oscillator and the damped harmonic oscillator, they have the solution of cosine function, but because this driving force set up some initial displacement, so that make the solution form with the sine function. But you can always actually convert it back to the cosine function by adding the pi over 2 as part of this initial phase. So it's not a big deal. So if you solve this one, if you plug back into this formula, then the maximum amplitude of this displacement with the externally forced harmonic oscillator would be expressed with this solution, f naught over m times square root omega square minus omega naught square plus b square omega square over m square. Okay, so here omega naught is angular frequency of the simple harmonic oscillation with the damping. I'm sorry, that this is simple harmonic oscillator. And then this omega, okay, so that omega naught is natural angular frequency of simple harmonic oscillator without damping, without external force, and omega is the frequency of external force. Angular frequency of external force. Okay, so the omega is control variable. You can control, you can change the omega or frequency because that's what you can add into that given system externally. So you can make this, let me change the color of this pen. You can make this, motor, just this motor. You can make this motor, external motor is running faster or slower, right? So you can just choose the frequency of this external force as you want. So this omega, angular frequency of system, or I mean the external force, could be controllable. So if you change, you scan the frequency of motor, and you can actually find out the maximum amplitude of a system. Do you remember what frequency it's actually just make amplitude is maximized, biggest number? I just told you like 10 minutes ago. So when was the condition, what was the condition to make that the amplitude x of this externally driving forced harmonic oscillator? So there are two frequency. Okay, there's two frequency. One is from the outside, one is inside. Inside frequency is natural frequency of a harmonic oscillator. That's omega naught. And there's external frequency out of motor, this motor, okay? That's omega. That omega naught already determined by the K of spring and the M of mass, right? There's nothing much you can do because already just fix the values. Once you pick up the spring, once you pick up the mass, then your natural intrinsic frequency is just already there. There's nothing much you can do. But you can change the frequency of speed of motor, right? You can make it faster, you can make it slower. So you can determine, you can decide this value of this omega, right? So now if you change the omega, the frequency of external force, then your amplitude of this mass m will change corresponding to the external driving force. And I think I already told you that the condition for maximum amplitude for frequency, what would be the frequency to make that external force frequency make the system displacement, like a displacement of mass is just the biggest. You can take a look at your note.
Yeah, I'm looking right now.
Yeah. I explained with this graph. Take a look at this graph. I just explained it with this one. So, or you can take a look at this solution out of the second order differential equation. That is actually this, you see that this plot, right? The left-hand side, this plot is an actual plot of this solution. Okay, so what condition of external force frequency makes this amplitude xm becomes biggest, largest? Do you want me to rewrite it?
Maybe, yeah.
Okay, let me just write it down one more time. So here, the maximum, so let me just write down the formula one more time. So the F, the net force out of Newtonian system is M times A, as you know, right? Here's net force. That is combination of Kx dV plus external force F naught cosine omega t. And this one, A, acceleration is the second order derivative of the x in time, and B is dx over dt, right? And now if you move this two terms out of the right-hand side to the left-hand side, then that should be m a x over d t squared plus b dx over dt plus kx equals f naught cosine omega t. Okay? So this omega is 2 pi f. And f is frequency of external force. So for example, if you set up the motor with the mass m, and that f is like the frequency of rotational motion of motor. Okay, so f. So now this is second order differential equation. This one is second order differential equation. If you solve this equation, that solution normally is known to be x times x maximum sine omega t plus pi naught, and that is omega is same frequency of this 2 pi f, the frequency of motor, and this one pi is initial phase or initial displacement condition. So now if you plug this solution back into this second order differential equation, you should be able to find the relationship between this xm and the m, b, x, k, and f naught. So x maximum displacement is f naught over m square root omega square plus omega naught square plus b square omega square m square. That is this x naught, x maximum. Maximum displacement of the mass m, this m. Okay, from the origin. Now, this omega naught is square root k over m. And this omega is, one more time, omega is frequency of external force, or the frequency of motor externally just driving the system. So as you can see, omega naught is constant value. If you choose, if you pick up the spring with the specific k value, spring constant, if you just pick up the mass, then omega naught is just normally just naturally actually just determined. There's nothing to actually you can control, right? But omega is external driving frequency, so you can actually change it. You can make motor rotate slower or run the faster. Okay, so the omega, here's omega is control variable you can actually choose. Okay, in given system, you have a mass m attached to the spring, and that attached to the external motor. So if you pick up the two k and m, under the circumstance that you already pick up the k and m, only things you can tune is the motor frequency, which is actually omega. Now, if you change that to omega, what condition make this value is maximum or largest number? So if you plot this xm with the frequency, then you can maybe just find out. So what condition do you think can make the xn becomes maximum value, largest number? Obviously, there's nothing much you can do with denominator, numerator, right? There's only this denominator term, especially in the square root. There's some combination of the variables make that it becomes what? 0 or minimum. So the second term is constant value, omega. And just take a look at the first term. If you omega getting close to omega naught, then this difference between these two numbers becomes smaller and smaller and smaller, right? That means your denominator becomes smaller and smaller and smaller. That make your whole number becomes larger and larger. Do you see what I'm saying? So the denominator inside of the square root, if omega, now this is omega, right? There's omega naught. This omega getting close to the omega naught, then this number becomes smaller and smaller. If external frequency is exactly the same as omega naught, then this first term becomes 0. Then this inside of square root will be the minimum number. Okay, you have some constant value, A and B, and then A becomes minimum, then number C becomes maximum, right? So if the frequency goes to the omega naught, then you have maximum value. But once it goes through this omega naught, then this one, first term, omega square minus omega naught square becomes smaller. So like going up, 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 and once it touches down to the omega naught, and that becomes smaller and smaller and smaller and smaller. So that make this magnitude of this placement become smaller and smaller and smaller. So when the external frequency of driving force exactly same as omega naught, you end up with the really large magnitude because all the energy from the external driving force or motor can be fully used to actually, push this mass back and forth oscillating. So energy loss becomes, negligibly small. Okay, so this is the call that the one you have, the omega naught, when the external frequency is the same as the natural frequency of system, that is called the resonance. So it's okay if you just not fully getting it, but you can just take a note it, and I'll explain later on when you actually your school actually move on to this chapter, and then I can just like get back to you, and then we can discuss one more time. But that I'm just giving you some conceptual overview of how this force harmonic oscillator actually works within certain condition. Okay, so external frequency, the driving force, is same as natural frequency. You have a huge magnitude of displacement of this mass m, because all the energy from the motor is used to move this mass m with the spring constant k. So that is maximum amplitude. Now you can also find the expression of the initial phase I, which is the function of also omega naught square minus omega square over omega times b over m. So that is the I of the initial phase, also that function of the initial frequency and natural frequency. All right, and one last thing I want to talk with you is the Q value. This is like a quality factor. Is sometimes called the quality factor. I show you now. There's like a resonance peak, right? Depending on the surface loss of this ground, that the force, all of the force could be actually plugged into the system at resonance, which is omega and omega naught, or most of the energy could be lost through the thermal loss on the surface of this ground if the frictional force is dominant. So if you have a lot of like a low surface and maybe you are just constant spring to the wall and you have like a huge K value, then this motor energy out of the external force will be mostly used to actually just compensate this surface energy loss, because this frictional force is so high that the system is not really movable. So most of energy is lost to the surface with the thermal heat. In that case, you have huge amount of energy spread over the large amount of frequency. So your the displacement pattern with the frequency, actually you can use omega, is like this. But if you have like a mirror surface, really flat surface, then your frictional coefficient is small, then the most of energy from the external force purely actually used to move this mass n. Very small amount of, only small amount of actually energy out of this external force is used to overcome that surface friction. So in that case, if you stay in the resonance condition omega naught, then you have huge resonance, a huge magnitude. So depending on the surface condition, so that's like a, or B, if B is small, B is large, then you have this kind of resonance frequency. This is XM. And if the mu K or B is small, then you have this kind of resonance peak of the displacement, maximum displacement. So depending on the surface condition or damping condition, you have really sharp resonance or kind of broad resonance. So the quality of this resonance could be parameterized with the quality factor, which is called the Q factor, or quality factor. And this from the half of the maximum value, this if it is like a, 1, you take a half of that, 1 or 2, and then connect to these 2 points. And that is called the bandwidth, like this, okay? So one more time, you pick up the maximum value of displacement and take half of it, and there might be the 2 point, let me change the color. So if you take the maximum and take, if you pick up the maximum point and then take half of it, then there might be the 2 point, the line actually, come across, and the 2 point, 1 and 2, difference between those two called delta omega, that is bandwidth. So this bandwidth for the large viscosity or large the damping term, has broad bandwidth, and this one, small damping term or small frictional coefficient, has very narrow bandwidth. If you take this one and take half of it, and there's 2 point that line come across, then the difference between those two lines is very narrow. So this case, let's say this one is narrow, this is wide, or maybe this one is 1 and this one 2. Delta omega 2 is much narrower than delta omega 1. So quality factor is normally just given by this definition. Resonance frequency divided by bandwidth. Okay, so it's indicating the how sharpness of the resonance. If this bandwidth delta omega is small, then Q is high. Bandwidth is high, large, then Q value is low. So Q value, quality factor of resonance, and the bandwidth is inverse relationship. Okay, so narrower the resonance has higher Q value, wider bandwidth is a lower Q value. So that Q value is sometimes used to indicating that the quality of resonance, if there's like a low frictional force or lower damping term with the harmonic oscillator, then that Q value is high. But if that system has the large frictional rough surface or large frictional force with a large amount of damping, then that has wide bandwidth, then Q factor, quality factor is low. So it is used to quantify the quality of the resonance of the forced harmonic oscillator. And this is the end of this chapter. And when you actually just start this chapter in the school, then I can maybe just give you another review on this chapter with your school print. But let's take a look at a few examples. Let me switch to the video file. And okay, I should have. All right. The first one. Example 14. Do you see my screen? I want to double check.
Yeah.
Okay. So hold on a second. All right. Just tell me if you trouble to actually see this screen. Car springs again. Determine the period of net frequency of the car. Example 14-1A after hitting the bump.
I can't really hear the video.
Can you say that again?
I can't really hear the video.
You don't hear the video?
Yeah.
Okay. Let me just replay then. Just tell me if you don't. Maybe I mute myself. So let me replay it. Okay. Example 14-2. Do you hear it? Car springs.
Yeah.
Okay.
Determine the period of net frequency of the car. Example 14-1A after hitting the bump. Assume the shock observers are poor, so the car will oscillate up and down. So in order to solve this problem, we have to take a look back. Example 14-2, 14-1. So the 14-1, let me just read that problem for you. Car springs. When a family of 4 with a total mass of 200 kilograms step into their